Hey, what is up everybody? It is Mr. Boylan, and it's gonna get a little bit toasty in here because for this video, we are going to explain the law of conservation of energy, define heat, and perform calculations involving heat, mass, temperature change, and specific heat. As always, breaking it down a little bit for you, first thing we're going to do is we're going to describe the relationship between temperature and kinetic energy, which hopefully you're a little bit familiar with already since it's something we talked about in a previous unit, but it's going to be super important for this unit as well. So we're just going to come back and refresh our memories. And then 2, we are going to explain the law of conservation of energy. And then 3, we are going to explain how heat is the transfer of kinetic energy from one object to another. Okay, so first we're going to go back to temperature. Temperature, remember, is the measure of the average kinetic energy of the particles of a substance. Energy of motion. Here's some particles. They're in motion. Some important things to keep in mind about temperature and its relationship to average kinetic energy. Remember that the Kelvin temperature is proportional to the average kinetic energy. So, for example, if you were to double the Kelvin temperature, you also are going to double the average kinetic energy. If we go back to our thrilling animation that illustrates particles in motion, remember that when you heat those things up, notice how that affects their average kinetic energy. Likewise, if you cool things down, recognize that they have less kinetic energy. Or if we cool things way down, they have even less kinetic energy. But again, remember that relationship is proportional. Okay, second thing to remember when we're thinking about temperature and average kinetic energy, remember when you hit absolute zero, the particles have zero kinetic energy. In theory, so if I drop this temperature down to 0 Kelvin, okay, recognize that we don't even have that vibrational kinetic energy anymore. The molecules have stopped moving. Third thing, just to keep in the back of your noggin, is that many times when we are asked to think about temperature as it relates to kinetic energy, we're going to be shown these Maxwell-Boltzmann distributions. And really, it's just a great way for us on paper to understand and recognize the relationship that exists between temperature and kinetic energy. And so as you take a look at your notes or at the Maxwell-Boltzmann plot that you see on your screen, simply recognize that when you have got a sample that is at a lower temperature, in this case 300 Kelvin, and you compare that to a sample that is at a much higher temperature, in this case 1000 Kelvin, recognize that those particles that are at the higher temperature are going to have a much higher velocity and therefore a much higher average kinetic energy. Maxwell-Boltzmann, thrill a minute plots. Okay, and then the last thing to keep in mind as you try to remember all of the glorious things about temperature is that many times when you're asked to interpret what's going on with particles and their average kinetic energies, you are doing this on paper for a test, and you're not having a really exciting time using some online simulations. Oh my gosh, this is so much fun! So what that means for you is that you are going to have to interpret the average kinetic energy that a sample has based on many times vectors. And vectors are just these little arrows that you see that indicate the relative kinetic energy that a sample might have. So as you recognize the image on your left, there are a bunch of vectors that are relatively short, indicating that they have relatively low velocities and therefore relatively low average kinetic energies, and therefore it's at a relatively low temperature. Whereas the sample on your right, we've got much longer vectors indicating much higher average velocities or higher average kinetic energies and therefore much higher temperatures. Okay, so while that was a thrill a minute down memory lane, we really are focused in this unit on energy changes that occur in chemical reactions. Thermochemistry. And so it's important to go back and refresh our memories on temperature because that's going to be a huge part of this unit. But there's some other really important things to keep in mind as we think about studying energy transfer. The first thing to keep in mind is that every substance has a certain amount of energy stored inside it, and the energy is stored in the chemical bonds of a substance, and we call that energy, that stored energy, the chemical potential energy of that substance. It's also really important, since we're going to be studying heat transfer, that we recognize there is a law that governs the fact that energy is neither created nor is it destroyed in a chemical reaction or a change of state. And that idea is going to be really important because a major goal of thermochemistry, a major goal of what we're going to do in this unit is we're going to examine the flow of heat energy between a system, usually the chemical reaction or the substance that we're studying, and its surroundings. You need to be able to recognize that whatever amount of energy your system has before the energy transfer, and whatever amount of energy your surroundings have before the energy transfer, when the transfer happens, heat is going to go into your system or heat is going to be given off from your system. Compare the amounts of energy after in your system and in your surroundings to what you have before. And even though you can gain or lose energy, the overall amount of energy in the universe stays the same. Okay, and when we are studying this energy transfer, we're really going to be focused on heat energy or thermal energy, hence thermochemistry, which we're going to represent with the letter Q. And it is the energy that transfers from one object to another because of a temperature difference between the objects. So one object has a larger kinetic energy, a higher temperature. One object has a lower kinetic energy, a lower temperature. And when you have a situation where something has a higher kinetic energy and something else has a lower kinetic energy, and when you put those two things together, you need to recognize that the kinetic energy is going to be transferred from the warmer object to the cooler object until the temperatures or the average kinetic energies are the same. And when you reach that point where the average kinetic energies are the same, we call that thermal equilibrium. Okay, so I'm going to play for you a thriller of an animation, but recognize that we're going to have something that is a substance that is cold or lower kinetic energy and a substance that is hot or higher kinetic energy. And we're going to put those two substances in contact with one another, and we're going to watch the transfer of heat energy until they reach thermal equilibrium. So again, cold, moving a little slow, hot, moving pretty rapidly. As we put those two things in contact with one another, notice that the heat transfers from the hot to the cold until we reach thermal equilibrium at the point where they have the same average kinetic energies. Okay, and that brings us to an end for today's video. Check out some of those amazing animations and videos that I used in the presentation.